in-place algorithms, we learned the definition before. What is an in-place algorithm? Storage usage. The extra storage space, other than the storage space you use for input data. Given input data, you have to use the minimum storage space to store the input data. So we don't count that part. But in order to work on your algorithm, you need usually you need extra storage space. That extra part, if we can use a constant number, no matter how large is the size, the data size could be larger. You can change the data size, but the extra part is always bounded by a constant. Then we say the algorithm is in place. All right. So that's the concept we learned before. Now let's look at the several algorithms we learned so far. Use this definition to check which one is in place, which one is not. Okay. So we haven't learned many, just a small number of algorithms. All right, so we review that definition. Right. First one, evaluate a polynomial. Our first problem, based on Horner's rule, we do it in this way. So think about, first, we need to store the input data. We need to use the minimum storage space to store coefficients, then the variable. We do not count that part. Okay? We do not count that part. But when we work on the multiplication, addition, look at the extra storage space we need. Temporary, we also count the temporary storage space. You need a temporary variable to store some intermediate values. Those you need to count. So think about, for that part, can you use a constant to bound it? Right? Yes. Yeah. One variable we can store this, temporary values. Then, constant. So this one is easy. Yeah. All right. Okay. So we can see easily, right? Yeah. Next one. Number 2, search an unordered array. Linear search, right? Let's look at the linear search. So given a key, so we go through each one, we compare, match or not. So the extra storage space, you can see very, constant, definitely constant. 0 or 1, we just need a constant.
Yeah. Would just need the extra data just be bigger than the index you found it, or what extra memory do you need?
Extra memory. All right, so the key, so we compare. Do you need a for loop, right? When you need a for loop, you need a counter variable, right? Things like that, okay? So anything you need to use, for loop, for example, Number 3, find the minimum number array. Also, right? So you can see easily. We scan once, for loop, right? Well, you need to use a for loop. Okay? All right. Number 4, sort an array. Depends on what algorithm we use. And we will learn several sorting algorithms. Some of them are in place. Some of them are not. So for each one, we need to really check if it is in place or not. Right? But the first one, selection sort. Yes, right? Yeah, selection. Yeah, because basically we apply this many, many times. Right? This one in place, we apply same thing several times. Yeah. So that one, no problem. Okay? So one extra space we can use for all these minimums. Only one extra space. Okay? All right. Also in place. Okay? Number 5, element uniqueness problem. Remember, yeah, element uniqueness problem. For this problem, we sorted first, right? We sorted first. Yeah. So there, you need to look at the algorithm you use to sort the array. Is that in place or not, right?
So generally, is this problem element uniqueness problem? What are you doing in this case problem?
In general?
Yeah. What were we testing again in the element uniqueness problem?
Right. General, if you do not specify what algorithm, it's hard to answer that question. Yeah, so that's good. So generally, if we say one problem, you have to say what algorithm do you use. Some of the algorithms you use in place, some are not. So you cannot just say problem, right? Problems, you know. So here, the algorithm we use, if it is in place, then that is in place. Otherwise, it's not. Yeah. But this algorithm uniqueness problem, this algorithm uniqueness problem, later we may have different algorithm to solve it. Okay? So far the sorting-based method is the best, right? So far. Later we will see we can do better. We do not use sorting-based. We use hashing. Hashing, we can do better than that. Yeah. So, but, you know, we need to learn that hashing first. Then we can solve this problem much faster. Yeah. All right. Yeah, so number 6, calculate the factorial. Easy, right? Yeah, factorial. Non-recursive way. Yeah. Okay. Also, yeah. So I think, right, but here, a small comment. For recursive algorithm, usually it is not in place. Recursive. Why? Because of the stack. Okay? You push into the stack. Okay? Yeah. So you start from n. In order to calculate n, you need to go to problem of n minus 1. Then n minus 2, then you keep pushing into the stack. The stack is very deep. That's the extra space, right? Yeah. The whole stack, that's the extra space. That's not a constant. Okay? Yeah. So that's, you know, usually in general, yeah, someone may argue, oh, I can use a special way, you know, can make it in place. I can say it is possible, but it's rare. Even if it is possible, it is rare. Yeah. But in general, not in place. So that's why you can see if we use recursion, the cost we pay very high. The cost we pay very high. Yeah. Storage space. We will use a lot of memory. Memory resource. We use a lot. Okay. Yeah. So that cost you need to be aware of. Okay. Yeah. All right. So that's the topic of, oh, what's that? Yeah, I explained that. Okay. Oh, I need to drag a little more. Right. Okay. All right. So that's lecture 5. Okay. Remember, we have 4 lectures for test 2. Our test 1 covering the first 4 lectures. Yeah. Yesterday I recorded 8 videos, 8 topics, so I hope you can find time to study, because those 8 topics very likely to appear in the test 1. Yeah, because I feel those are important. So I select those 8 topics most important. So I explain. Okay? Yeah. So you can expect at least 6 or 7 questions from those 8 topics. Okay? 6 or 7 questions from those 8 topics. Yeah. This is lecture 5 for test 2. Okay? Yeah. 5, 6, 7, 8. 8 lectures for test 2. Yeah. Now let me switch to